Here's the second part of section 10.3. We're going to do a couple of examples of series just to get one more look at how these things work. So suppose I looked at a series like this. I've got the sum from n equals 1 to infinity of 4 times 3/4 to the n minus 1. Well, first of all, I know that this series is geometric. It's in the form of ar to the n or ar to the n minus 1. I also know it's an infinite series because the upper limit up there is infinity, and so I should keep adding terms forever and ever. I also can figure out what the ratio is. If I look at this value here, that r value is 3/4, so because the absolute value of the ratio is less than 1, it converges. Great. What is the sum of my series? So to find the sum of that geometric series, I'll use a over 1 minus r. So the first term, if I put a 1 in for n, right, because that's what the directions say, it says start with n equals 1, put a 1 on the top there for n, 1 minus 1 is 0, and so a is going to be 4 times 3/4 to the 0 power, which is 4, right? 4 times 1 is 4. I get 4 over 1 minus 3/4. So that gives me 4 over 1/4. Hit the top and bottom with a 4 to clear out that fraction over there. And when you do that, you'll end up with 16. So that's the sum of my series. So the series converges. What does it converge to? Converges to 16. So if I add up enough terms, that series will begin to approach 16. All right, let's try another one. Identical problem, except this time we'll start with n equals 2 and go to infinity of, again, 4 times 3/4 to the n minus 1. So in this case, my first term is going to be 4 times 3/4, right? Because if I put a 2 in for n, 2 minus 1 is 1. So 4 times 3/4 to the first power is 3. All right, let's try that a over 1 minus r formula again. So the first term is 3 over 1 minus 3/4. That gives me 3 over 1/4. Same deal as before. Hit the top and bottom with a 4, and I get 12. So now that's a different answer, right? The previous one summed up to 16. That one only sums up to 12. Why? You realize that by changing that index from a 1 to a 2, you're basically leaving off the first term. Well, the first term here was 4, and the 4 that you left off is the difference between an answer of 16 and an answer of 12. So that does make a difference where you start that. All right, let's take a look at another one. Suppose I have the sum from n equals 1 to infinity of e to the negative n. Well, first of all, is that a geometric series? Isn't this the same thing as the sum from n equals 1 to infinity of 1 over e to the n? And isn't that the same thing as the sum from n equals 1 to infinity of 1 over e to the n? Ah, now it's geometric with a ratio of 1 over e. Well, e is about 2.718, so 1 over something close to 3 is definitely less than 1. Okay, so that thing should converge. All right, next question is, what is the first term? Well, the first term would be e to the negative first, which is 1 over e. And so when I set up my a over 1 minus r, I get a over 1 minus r. Well, as funny as it looks, let's hit everything top and bottom with an e. All right, so when I hit everything top and bottom with an e, I get a 1 on the top and an e minus 1 on the bottom. That's the sum of my series. All right, so this thing also sums up, in this case, to 1 over e minus 1. Even though it didn't look geometric at first, play around with it a little bit and turn it into something that is geometric, and sure enough, it works. All right, let's try another one. Suppose I take the sum from n equals 0 to infinity of 4 times 5/4 to the n. Well, this is geometric, right? It's in the form of a sum of ar to the n, but here's the issue. That 5/4 is greater than 1, so this thing diverges. My warning is, if you had tried to apply that formula, the a over 1 minus r, you'll get a number. It just won't mean anything. Okay, let's take a look at one more of these. This one is a little bit different because I'm going to look at the sum from n equals 1 to infinity of 2 times negative 1/3 to the n minus 1. Now, is this geometric? Sure it is. Even though that ratio over there is negative, all that means is that it's going to keep alternating back and forth, back and forth. But remember, the rule was that if the absolute value of r was less than 1, then it converges, and sure enough, the absolute value of r is less than 1, therefore it converges. What does it converge to? A over 1 minus r. So what's the first term? Let's take a look at that. The first term is going to be 2 times negative 1/3 to the 1 minus 1 power, or the 0 power. So the first term is 2, and the constant ratio is 1/3. So a over 1 minus r gives me a over 1 minus a negative 1/3, which is 2 over 1 plus 1/3. All right, so if I have 3/3, and I add another 1/3, I get 4/3. Ooh, invert and multiply. 2 times 3/4 gives me 6/4, which is 3/2. So even though this alternates back and forth, you realize the first term is positive. So as it alternates back and forth, the sum of that series is going to end up being positive as well. So in this case, even though it's an alternating series, back and forth, it still adds up to a over 1 minus r, which in this case, 3/2. All right, one more type of series to take a look at in this section, and that is this one. Let's take a look at the sum from k equals 1 to infinity of 1 over k plus 1 minus 1 over k plus 2. So this is one big series, starting with k equals 1 and moving up. All right, for lack of a better thing to do, let's start making a list of different terms. So if k is 1, 1 plus 1 is 2. Okay, so I get a half minus a third. If k is 2, I get a third minus a quarter. If k is 3, I get a fourth minus a fifth, and you can start to see the pattern, right? If k is 4, 4 plus 1 is 5, so I'll get a fifth minus a sixth. Great, let's write out the whole series. I get a half minus a third, that's from the first term. Then I get a third minus a fourth, that's from the second term. I get a fourth minus a fifth, that's the third term. I get a fifth minus a sixth, and then it keeps going. We have a name for this. We call this a telescoping series. Because if you think back to those old-fashioned telescopes like you would see on a ship from like the 1700s, and each of those lenses gets smaller and smaller and smaller, that's what this is supposed to look like. Because if you look at the terms of my series, they're getting smaller and smaller and smaller, right? I got a half, some thirds, some fourths, some fifths, some sixths. As those denominators get bigger, the series itself gets smaller. Now, a funny thing happens. If you take a look at the series here, these two terms zero out. These two terms zero out. These two terms zero out. So what is my series adding up to? It turns out my series only depends on the first term and the very last term. So I'm looking essentially for the limit as k approaches infinity of the first term here, which is a half, and it's always going to be a half, right? So the first term is a half, and then it's going to be minus the last term, which is whatever 1 over k plus 2 is. Well, as k approaches infinity, this thing here approaches 0. And so the sum of the series is a half, and the series converges. So this is a telescoping series in that these things get smaller and smaller, and you notice the way it's set up is that those inside terms all cancel, so that you're only left with whatever the first term. In this case, it would be the very first value here evaluated at k equals 1. So again, it's important to make sure that you pick the right k value here, right? K equals 1. Substituted in here, that becomes the very first term. The last term is whatever 1 over k plus 2 is as k approaches infinity. Therefore, this thing converges, and it converges to a half, that same half that's at the very first term. All right, that's the end of 10.3, the Intro to Infinite series.